Please start. Please start.
Shall we say? Hello everyone. Hello everyone. Good evening. We are here to present our basic background work, basic background research work which we have done regarding our project which is allotted to us. And the project which we are working upon is optimizing the data set for multilingual representations. And we have selected three research papers which we are going to present each one of us today. And these we have found these three papers which are more relevant regarding the dataset optimizations and the subset selections, and we will discuss the algorithms and the key takeaways and the challenges which these algorithms solve and the relevancy to our project, which is data set optimization. Yeah, so the first problem which I'll be for the first paper which I'll be presenting is submodular mutual information for targeted data subset selection. So the key concepts which we will be looking on in this paper is that we will be looking on submodularity, submodular mutual information, and targeted data subset selection. So we will see the definitions of them in the following slides. So what challenge are we trying to resolve here? What is the challenge which is presented in the paper? The challenge which is presented in the paper was that we have a huge data set and we have many labels in them. So there might be some labels or there might be some slice of a data which are like some classes which might not be trained properly in a model. So we want to find out what those classes are, which is basically the subset of the whole data set, and we want to retrain the model on it so that we can improve the efficiency of our model. So how are we doing it? So we are doing it using our submodularity function, which defines as, so it is a set function which is from a power set of v to real numbers such that it follows the following equation, which is basically if we have three sets such that x is subset of y, which is subset of our v, which is our ground set. So if we add any element e which is not in y, if we add that element to a subset x, and if we try to check the gains, like if we try to check the difference between the functions before adding the element, after adding the element, and before adding it, and if we try to check the gains, then the gains will be more for subset x rather than subset y. So this property is known as diminishing returns property. So we are going to use this property in another function which is our base function, which is used in the algorithm. So what is this diminishing return property tells is that if we have, when as a subset size increases, the gains decrease. So when we add any element to a larger subset, the gains will be less as compared to a smaller set. So this is what, so a function which follows this kind of value, this kind of property is known as submodular function. So next we will look on to submodular mutual information, which is the base function which we'll be using in the algorithm. So what does this tell? So sub SMI is represented as I on a modular function f on two subsets a and b. So here we will so here this actually gives us a measure of what is the similarity in the both data sets, like what is the similarity shared between the two sets. So here we can see that here if we look on the diminishing returns property, if a and b are similar, then there won't be much value added to f of a union b, because since they are both similar, if we since the classes of both the data are similar, so there won't be addition of more data points, and therefore this set will actually have a less value as compared to when they are different. So when they are different, this A union B will be more value because it is a monotonic function, and since they are not different, so there will be many classes which will be added, and this is the, and this value will get decreased more, and therefore it will have a high value. So when two sets are similar, then we will have a high SMI function, and whereas when they are different, then we will have a low SMI value. So we will use this property of this SMI such that we will take a data set and we have a target class. So when we are trying to take a subset of our data set, which is a some classes of the whole labels which are there, we will try to check with a target class. So we know that there are some biased class or there are some underrepresented class, and we would like to retrain our model on specifically on those only to improve the efficiency. So for that, we will try to take a target class, which is basically the classes which are similar to these classes are underrepresented, and we will try to remodel on this. We will try to train a model on this. So when we, so this is a target class, and this is B over here, and A is our target class, which is from the ground set, and we will take a subset from it, and from them we will try to check the where the submodularity is the maximum. So when the submodularity is maximum, those two classes are very similar in nature, so we can train the subclass of it in A to improve our efficiency. So these are the examples of SMI functions. We can see that there is a graph cut modularity mutual information, and faculty location mutual information, and log determinant mutual information. So these three functions are generally used in such cases. Yeah, so this is the objective of our algorithm basically. So the objective is that we want to select a subset of unlabeled data that maximizes the similarity to T using SMI. So what do we do? The steps are here as follows. We will train the model on the initial ground set, which is here represented as epsilon, and we will compute our gradients using the corresponding loss functions of U and T both, and then we will use gradients. We will use these gradients to compute the similarity kernels. So what is a similarity kernel? So similarity kernel is basically the matrix which tries to take the similarity between two matrices between two sets in it. So this similarity kernels uses SMI. So this SMI is used in similarity kernels to get the similarity between two indexes, and we will maximize this similarity kernels which use SMI, and then this returns our subset A cap which we wanted, and we will retrain our model on A cap, which is the subset which is closest to the target set. And this is the model which was given in the paper, and and if we see the fourth step here, we will try to maximize this function which is your SMI of A and T, and we will also add a diversity function. So this G of A, as we see in the third step, using the gradients, compute the similarity kernels and define a submodular function and diversity function G. So what this diversity function G does that, if we try to take a set, we will try to take a subset which is diverse in nature. Like it should not be confined to a biased only some kind of classes, and there shouldn't be any bias in them. So we will add this diversity function to try to maximize the inclusion of all kind of classes in it. And then we will obtain the labels of A cap. This A cap is the data set which is very much in similar to T, and we will obtain the labels of it, and we will again train the model on it. And these are the data sets and the baselines which are, this is the data set which this was trained on, and these are the baseline functions which were used before SMI and TSS, like uncertainty sampling or random sampling or batch or this. Yeah, and the summary and the key takeaways are, so if we take the improvement in the, if we try to train on an unlabeled set, and if we try to check the improvement in both the trained and the retrained model, the improvement is 20 to 30% in the accuracy of it, and this is also 12% higher than the baseline cases which are used like random sampling and other things. And the overall accuracy of the model is increased by 2 to 6%. So the implementation process, if we try to take a summary of it, this is as follows. We will take a when it was put into test, this was how it was implemented. So we will take a biased training data which has only two classes as biased, which is intentionally kept to test it. So it was underrepresented, and we will improve its model's performance by applying this on a large data pool. We will take a huge data lake which has a huge number of classes, and in them we will introduce bias on two, and we will give a subset target class which has two labels, and in them we will try to generate a label class of it as we have seen the algorithm. And we will read, and using the similarity kernels which uses the SMI again, and sorry, not again, which uses the SMI to find the similarity between the classes and returns it, and we will retrain on it, and this is, and then the improvement happens. So this is the algorithm of the paper which it tells, and these are the key contributions. Like this, the key contribution is that it increased the model's efficiency to a larger extent, which is currently used now. So over to the Pawan for the next step.
Can you hear me? You can't hear me, it looks like. Can you hear me now?
Hello, everyone.
Yes, sir, we can.
Okay, so I just have a very quick question. Under what conditions? Actually, two quick questions. One is, what are the baselines on which the improvements have been shown of the SMI methods? And are you able to talk about the conditions under which the SMI functions are actually submodular? Is there any characterization in the paper itself? Two questions. What is the baseline here on which the improvement is claimed? And second is, under what conditions are the SMI functions actually submodular? Yeah.
So regarding the first question, which is regarding the baselines. So baselines are like the current, like before this algorithm was proposed, these were the currently existing models which were used to do this retraining of certain targeted classes. So these are the base, so that they are called as baseline, and initially they were like uncertain sampling, which used entropy sampling entropies to kind of use the sampling entropies instead of SMIs here to get a similarity. If the entropy is maximum, then there will be more similarity, those kind of properties which was over there, and on them it used to do the retraining. So those are the baselines over here. And regarding the SMI properties, so for a submodular function, the key four properties are that it should satisfy the equation, and it should be monotonic in nature. Like if we add x is subset of y, then f of x should be less than or equal to f of y. So these are the two key properties of it.
Yeah, but I'm asking you, under what conditions? For example, the SMI function is a submodular when the original function is, say, disparity min, or is it submodular when the original function is determinable point process? Is it submodular when the original function is facility location? This is submodular when the original function is graph cut. What happens, for example, when the original submodular function is original base function is graph cut?
Do you mean like original objective function is whether submodular or not? Kind of.
F. If f, the function f is graph cut. Let's take a specific example. What does the paper say when f is graph cut about the submodularity or the nature of f of x union e minus f of x? Sorry, f of what I meant is the information gain variant of f. Right? So can you go back to the information gain variant of f? Can you go back to the slide which had the information Yeah, exactly. So if of x comma y or a comma b, if it's defined as I of x comma y or a comma b, I of a comma b, let's say, is f of x plus f of y minus f of x union y, right? Or f of a plus f of b minus f of a union b. In such a case, I'm talking about the definition of I. Go back to the definition of I. Go back to the, yeah. So I'm saying if f is graph cut, what does the paper comment about the nature of I or any of the other variants? When f is specific location, what is the nature of I?
So you like if we have two, if you say two sets are like two graphs A and B, then what is the nature of I? Is that what you want?
Right. Not graphs,
Okay,
graph
yes,
cut.
like I
Graph
not in
cut.
the context
I'm
of
not saying.
graph, but in the context of facility mutual information, then I read about it in the paper that regarding the facility, like facilities, it is like basically if you have a room and if we have an event and if we have some function stalls, so where do we need to keep the function stalls? And we have a huge set of stalls. How many stalls are actually relevant to cater all the audience needs? Like that is how they gave example in the paper. So over there they use like A and B as two sets, and in them they will see only those sets which are like more relevant to it. Like if we increase the value of those stalls, then this I will decrease because because of the diminishing returns property. Like that is one instance which was told in the paper regarding this facility mutual index, but graph cut I don't remember anything.
Okay, why don't you go back to the paper? There's a very important question I'm asking you. Possibly you're not understanding my question. You're trying to explain what is the nature of f when f is a facility location. That's not what I'm asking you to define. I'm asking you what is the nature of I when f is facility location. But let's pause it. Is there any? Please continue, and the students and the audience could also ask questions. Please continue to the next paper. I don't have anything more unless students have more. But my question is not completely answered. So you may have to go back to the paper to answer my question properly. Nature of I when f is of a particular kind. That is what I'm asking. I didn't ask you to define f.
Oh, got the question, sir, but I think
Yeah,
I will need to
go.
go to the paper and
Sure.
check it regarding.
Yeah. Next paper, please continue.
Shall I start?
Next
Start
paper.
my paper.
Next paper. Yeah, please. Next paper.
Okay. I am presenting you the second paper. This is also based on subset optimization, but using different approach called gradient match. Coming to the intro, problem statement is generally modern machine learning training data sets are very large. So training with these massive data sets are computationally expensive. So we definitely need help of a subset of data set so that subset information of the subset is approximated as information of the data set. So proposed solution, we will select a subset of the data set whose gradients closely match with the gradients computed by the complete data set. This was we are selecting the subset using the help of OMP algorithm, and we also defined an error function. I will explain you the error function. The first term is basically gradient of the loss function using the selected subset. I mean, a weighted gradient of the loss function using the selected subset. These weights are these weights are on the each point on the selected points on the subset, and the second term is gradient of the loss function using the complete data set. So the objective is to minimize this error function so that the weighted gradient of the loss function of the subset data set is closely approximated to gradient of the loss function using complete data set. Also, they introduced a regularization term just to ensure not to overfit the training. And coming to the algorithm, objective is already explained. Like we should accelerate deep model training while maintaining accuracy by selecting the subset of the data sets. And let me say a brief on the algorithm. These three steps are the key steps. One is periodic subset selection. Like for every R approx, we will get a subset using OMP algorithm, and this OMP algorithm is greedily selecting the points from the entire data set and put on the subset. And we are using weighted training. I mean, we are training the selected subset within optimized weights. This OMP algorithm gives the subset and the weights corresponding to the subset. Let me explain the gradient match algorithm. You can see here for every R epochs, we are getting the subset from the OMP algorithm. Here is valid equal to 0, is valid equal to 1. Basically, whether to select the subset using validation dataset or not using validation dataset. And if the epoch is not a multiple of R, then we are using the subset which was computed previous iter. And here theta t plus 1, basically we are training parameters using the selected subset. Basically, this was an adaptive data subset algorithm. This means basically in traditional approaches, we will select a subset and then we will train the model. But here, while training only, we will select the subsets. So this was different from traditional approaches. And how we are selecting the subset is basically we are using OMP algorithm for it. In OMP algorithm, we are starting with the subset with null set, and then of course I introduced an error term. This was the gradient of the error term, and here mod x is number of elements in x is less than equal to k, and error function is less than equal to epsilon, means they are also introducing a break terms. Now they will include those elements which was maximizing the gradient. I mean, they want a much difference while keeping a point in the subset, and they also getting weights from the OMP algorithm using minimum. These was obtained by the minimizing the error function, and those corresponding weights in the subset they are returning. Coming to the key findings of the paper, I introduced these three terms. I mean, speed up, energy efficiency, and accuracy. Speed up is reduction in time, and energy efficiency is reduction in computation. Accuracy drop is there must be an accuracy drop because we are not using complete data set. We are using the subset of the data set, so there must be an accuracy drop. These are the results. I mean, after using subset selection. Okay, selecting a 10% subset, we are getting a speed up 7 times, and there is an accuracy drop of 2.8%. And selecting 20% subset, we are getting 4.2 times speed up, and there is accuracy drop of 1.5%, and 3 times speed up when we use 30% subset. And I am also explaining the brief about third paper too.
So I have a question for the second paper. Can you hear me?
Yes, sir.
So I'm kind of comparing the second and the first paper. Okay, the first paper you were specified a function f, and you had an mutual information variant of the same function, right? And the goal was to identify or maximize that mutual information function. Given an A, you are trying to select a B, right? Conditioned on a given query set, you are trying to say maximize the information gain obtained by selecting the subset from the ground set. That was for a very fixed form of F and its way corresponding mutual information variant I. In the second paper, there are, as I understand, there are multiple variants, right? I mean, this, of course, I'm a co-author in both papers. So the second paper that you presented, right, the error function. So there was potentially a validation. Let's look at the, you know, right? The second paper had a case where the one of the data sets is a validation data, right?
Sir.
Hello?
Repeat once.
What?
Repeat, sir. Last
Yeah,
statement.
LV, right? Or LT, comma LV, right? You could have identifying a
LT,
subset of
LV.
the correct of the training set such that the gradient matching is with respect to the validation loss gradient, right?
Yes, sir.
So this thing, you can think of this validation set as the query set. That's one interpretation, right? There's a validation set as a query set, and I'm trying to identify a subset of the ground set, which is the training set.
Yes, I means they are taking two types. One is validation data set and training data set. So
Yes. So my one question I have for you is under this very restricted setting, query as validation and the ground set from where you're trying to identify is the training set. Ground set as training set. What is the
yes,
fundamental difference for this specific configuration of a query as validation and the ground set as a training set? What is the fundamental difference between these two papers for this specific setting? What do you understand?
basically we will use validation data sets not to warp with the data set. So that might be the reason in this. Means using only training data sets, these selecting a subset may warp with the data, right?
No, that is okay. You are explaining the purpose of the validation set. Fine, I agree. I'm asking the difference between the first paper you presented and the second paper you presented in terms of their effectiveness when you have this specific setting of validation set as a targeted set or the query set, right? What are they achieving different things? You are talking about the general thing when why is validation set to be used as a query set? My question is the paper 1 and the paper 2 you presented, how is the effectiveness going to be different? For the specific set, for the specific query set or targeted set.
Yes, means we are using different loss function here. Means here we
Okay,
are
so your
using
point is,
error.
go ahead. Okay, so you're saying we are using a loss function and its gradient here, right? You're using the gradient.
Yes, sir.
Gradient matching is what you're doing. What
Yes.
are you doing in the first paper? In the first paper, what are we doing? Does in this first paper,
Yes, sir.
the information gain, is it in any way connected to the loss function that you optimize? See, remember there in the second paper, there is one more optimization going on. The optimization in the second paper is also with respect to theta. You're learning parameters theta associated with that loss function, right? Or trying to minimize
Yes,
that
sir.
loss function. Is there any such notion in the first paper? is there any notion of loss, machine learning loss? Like we talk about logistic loss,
So here is
support
the
vector,
first
hinge
step of the
loss.
gradients were computed using the loss function. Like only the gradients are computed, but we are not like you are not. We are in the second paper we are using the loss function to take out the subset of our ground set. But whereas in the first paper the loss functions are used as a gradients, which will be used in the SMI function.
Right. So you see in the first paper, there is no direct connection, it's very indirect. The loss is used to compute the gradients, and then the gradients are used to compute the similarity function, which is then used to basically right maximize the information gain indirectly. Whereas in the second, you're trying to solve for both of these together. You're trying to learn the parameters theta, which is the loss, such that gradient matching happens, right? Or gradient
Yes,
matching
sir.
for the subset of the training set with respect to
Yes.
the validation set in this specific setting.
Ah,
Okay,
yes.
yeah. See, I would like you to think a little bit more deep like this. Okay, good. The question was to trigger your thinking, and I'm assuming Priya and other TAs do ask such questions so that the thread connecting the different papers also becomes clear, at least in specific settings. We should not be doing apple versus orange comparison, right?
Yes, sir. Got it.
Okay, go ahead. Next paper. Unless the audience, unless somebody from the students want to ask, yeah, or TAs also want to ask. Go ahead.
Mm.
Go ahead. Third paper. Can you proceed to the third paper?
Okay. Once repeat the question. Architecture, you mean? Architecture and data.
You can go to the third paper. Oh, someone is asking you a question from the audience.
Yes, yes.
Uh,
Yes, please repeat it. Architecture is used for subject selection in grammars. Yes, which architecture? Grammar.
like means we didn't concentrate on the architecture. Means we understood the algorithm and not proceed on the code. So we didn't, means we need to look up on it. As of now, we didn't. So I would like to give a brief on thought paper 2.
So as I understand, the question from
Basically,
the audience was the ML architecture in the second paper. What was the right? And you're saying that's something you did not look at very carefully. But
yes.
that's at least,
Huh.
yeah. Since there's an ML optimization for ML, it'd be nice for you to be aware, right? What was the, well, you may not have all answers to motivation for the choice of the architecture, etc. But it's important to be aware. Please do that. This is I think an important feedback
Huh.
as well.
Got it.
Another important feedback. Go
And
ahead.
I would like to give a brief on thought paper 2. This was on distributed larger than memory subset selection with pairwise submodular functions. Here the problem is, what if the selected subset is too large? I mean, you can't, if the data set is 13 billion points and subset is also in millions, so storing the complete subset in a central machine also computationally expensive. So this was the main problem explained in this paper. And here also they introduced two traditional methods. One is centralized algorithm and distributed methods for subset selection. Centralized algorithm is basically training the complete data set. Means subset selection is completed in using only one machine. Distributed methods is we are distributing the complete data set into several machines and selecting the subset from the several machines and storing the subset in central machine. But this was the main problem in these two approaches. So they also proposed a solution which avoids the need for a central machine. Means subset selection is done in a distributed manner. And this was they also introduced a function, a score function, which was left side term is utility of v and right side term is means this was focused on diversity. U of V is basically utility of a data point V. Alpha is the weight of single utility term. I mean, you can say alpha sigma of U of V is the weight given to utility, and beta is the weight given to the diversity term. And these control the trade-off between utility and diversity. And high alpha focus on utility, and high beta focuses on diversity. And I'm hand over to Charan Singh.
I have a question there. Hello, can you hear me? Hello,
Yeah, Pratik has a question. Can you hear Pratik?
hello, can you hear me?
Yes, you are audible.
If you go to the previous slide in the equation, so this similarity is between V1 and V2. So you get a similarity matrix, right? Like between different points V1 and V2 that is part of the subset S. Okay. So am I? Yeah. So my question is that the similarity uh, uh, value S between V1 and V2 is basically a similarity score between 2 points V1 and V2 coming from the subset S, right? So can you comment on the matrix capital S that form based upon different such pairwise similarity scores? So for all pairs in V1, V2 in S, capital in the subset S, you get a similarity matrix. So can you comment on whether it's a positive semi-definite matrix or any other properties of that matrix?
Here we are introduced similarity term because you can't get a subset with only using utility, because if you only focus on utility, then you can you may miss the diversity term. Means,
Yes, yes. I think my question is not on why the motivation of using the similarity score. What I'm trying to ask is like any properties that you see in the similarity matrix, because that actually can also determine which type of algorithm you can use to optimize on. So any properties do you see from the similarity matrix?
oh,
semi-definite possible లేకపోతే అది ప్రాపర్టీ దానికి similarity matrix లేదు
it might be positive different. We should check up on it.
Okay, so you need to get back with them, understanding if there's a connection. Go ahead. Go ahead.
Yeah. So I'll be explaining about this, about what the algorithm was used in the third paper. Basically, there are, large scale data sets nowadays. We all know that, and so the computational costs and the computational costs are high, and even with the memory overhead too. So for this we need to select a high quality subset. High quality in the term aligns with selecting a subset which aligns with the what we have to do. And for this we use some modular function as before. And basically the what we are doing is, the algorithm provides us, there are two parts of the algorithm. One is the bounding algorithm and another is the distributed bounding algorithm. In the bounding algorithm, what happens is, basically there are two steps which are known as grow step and reduce step. It iterates between these two steps until the subset which we need and the subset
and the original data set which we need converge. In the reduce step, what we will be doing is we'll be reducing the original data set. We will be removing the points from the original data set which are not useful or unimportant to us. And in the grow step, what we'll be doing is we'll be adding points to the subset which are more important or highly likely
to be in the data.
to be in the data set. And for the bounding algorithm goes like this. First we calculate the minimum utility and maximum utility of the points. The minimum utility is what the minimum utility is basically the worst case scenario when it's contributed into the subset, and the maximum utility is the best case contribution scenario. We calculate this for all the points, and next this is the formulas which are used for calculation. Minimum utility is basically calculated in the neighborhood set and also in the subset which we are trying to form. And for maximum utility, we only have to check it upon the subset which we have to find. So the algorithm goes like, we have to calculate this for all points. The next step is a reduce step. Yeah, we will be comparing Umax or maximum utility of the point with the kth largest minimum utility. If the utility is less than the kth largest utility, then we'd be discarding the point from the original data set. And if like this, we get a set of points. And in the next step, which is the grow step, what we will be checking is we will be comparing the minimum utility of a point with the kth largest maximum utility of the point. If it's greater than that, then we would be considering that point too. And here k determines the threshold for elimination. Basically, a k is what the selected subset size has to be. These are just the algorithms which are used and which I have just explained. Normally, while checking in the normally while checking in the grow step, what we are doing is we are comparing in the right hand side of the negative sign. We are checking that in the subset V union S dash, which might be a too complex or in the sense of time. So we are taking a subset of the neighborhood to calculate and named it as the expected utility. And this neighborhood can be selected in two ways, which is one is uniform sampling, in which the neighbors are chosen randomly, and weighted sampling. The more important neighbors are selected with a higher probability. After this bound algorithm, another algorithm is used, which is the distributed greedy algorithm. In this mainly is used to partition the data set and run it on different machines, as Pawan explained, so that it reduces the time and also avoids memory overhead. Basically the algorithm goes like, first we have to partition the data set, then do greedy algorithm on each machine or each partition, and then we have to repartition again, merged, and the selected subsets are merged, and again you have to do this until we achieve the selected subset size. The algorithm goes like this. Basically, we take a partition cap of mod b by m. Here, mod b is the cardinality of v, which is the ground set. M is the number of machines, and r here is the number of rounds which we do this. And round is basically the number of points which we have to consider it's calculated by the delta function. M round is the points by the partition cap. I mean, the number of points we have to consider in the partition, in each partition, and we do a greedy approach on all these partitions. And again, I mean, repeat this until we get the selected subset size. We have done this experiment. I mean, in the paper they have considered a 13 million data set and 16 partitions, in which we take 350 GB per partition. The performance is tested for 1, 2, and 8 rounds with a factor of alpha equal to 0.9. And for the 10% subset selection, the scores are like near 1 billion to, for one round, the score is like 1 billion, and for 8 rounds, it has increased to 1.1 billion. For 50% subset selection, the score was from, for one round it was like 4.17 billion to, and for 8 rounds it was like 4.25 billion. And the number of points which were included from the original data set into the subset was almost 0.007% of the original data set size, and 10 points were excluded from them for exact bounding. And while using approximate bounding, since the constraints are a little bit soft, more points could be included, so that increased the number of points to 0.7% of the original data set and has excluded 60% of the points. We observe a trend that as approximation guarantee, I think it's at least 50% approximation guarantee. We can observe the trend that as the number of rounds increases, the score also increases. And again, the score is calculated by the formula. The score is calculated by this formula. Basically, it's a model objective function. More is the score, then it just says that the subset is more optimal. The takeaways from this are, bounding algorithm reduces the data size efficiently, and the approximate algorithm is same as the bounding algorithm, but it just partitions the data set. And after this, distributed greedy selection algorithm is used, which partitions the data. This, I mean, bounding algorithm or approximate bounding algorithm, both of this and distributed greedy algorithm is used, and they are run sequentially. And because of the partition, it avoids memory overhead, and it is scalable for points up to 13 million or even more. Oh, sorry. Okay. Basically, first we take from the data set, we reduce the size using the bounding algorithm, and there might still be points which are left in the original ground set after removing those points, and there are points in the subset which there are no points in the ground set in which there are in the subset we have taken. So basically, I think the greedy algorithm combines these two and does the partition.
In ground set, if you think of V points, on shrinking and gaining the points, we have the subset part and the the data set which are left enough, and then you will use this greedy approach to refine these points actually. So these two algorithms are sequential, one after the other we should do.
Okay. And does it theoretically, are there any implications of going around this shrinking, expanding, basically this iterative approach? Have they shown any theoretical properties?
Theoretical properties in the sense.
Does it converge? How much within
Yeah,
the optimal is this greedy? How good is
yeah,
this approximation?
the approximate they say convergence proof for the they say approximation. Approximate bonding. There's a proof for approximate bonding why it works. We haven't included that in the presentation. And we do the bounding algorithm until the ground set and the subset converge. I mean, there can be
Okay,
no
fine.
possible changes after that.
Okay, fine. I think we should move to the next presentation. We are severely overshot, right? So next presentation. Thank you. Thank you. Is the next team going to present now? Hello?
Yes, sir. Next one. Yes, who